Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Have you ever considered that what we see is only a tiny fraction of what's actually there? Think about Jupiter, that swirling striped giant dominating our night sky. You see the clouds, the great red spot, maybe even the shadows of its moons. But what if I told you that Jupiter is singing a song you can't hear, radiating a symphony of energy invisible to your eyes, a chorus of radio waves that reveal a hidden world of magnetic fields, charged particles and colossal electric currents? This isn't just some abstract astronomical fact. It's a gateway to understanding the very fabric of space, the dynamic interplay between planets and their environment, and the fundamental forces that shape our solar system. Jupiter, in this sense, is a giant laboratory, a cosmic experiment constantly unfolding before our eyes, or rather, before our radio telescopes. The light we see is just the visible surface. The radio waves are the whispers of its inner workings. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. So let's dive into Jupiter's invisible symphony. Most of us are familiar with the electromagnetic spectrum as a rainbow of colours, from red to violet, but that's a remarkably narrow view. Visible light is just a tiny sliver of the broader spectrum, which extends far beyond what our eyes can perceive. On one end we have high-energy radiation like ultraviolet, X-rays and gamma rays. On the other, we have lower-energy radiation like infrared, microwaves and radio waves. All of these are fundamentally the same thing, electromagnetic radiation travelling in waves and carrying energy. The only difference is their wavelength and frequency. Shorter wavelengths mean higher frequency and higher energy. Longer wavelengths mean lower frequency and lower energy. Radio waves, the focus of Jupiter's invisible symphony, are at the extreme low energy end of this spectrum. They can have wavelengths ranging from millimeters to kilometers. That's a vast range. Imagine a wave stretching for miles. That's the kind of scale we're talking about. But how does Jupiter, a planet of swirling gas and colourful clouds, emit these radio waves? The answer lies in its powerful magnetic field, which is the strongest planetary magnetic field in our solar system, dwarfing even Earth's. Earth has a magnetic field too, and it protects us from harmful solar radiation. But Jupiter's magnetic field is on a completely different scale. It's about 20,000 times stronger than Earth's and extends millions of kilometers into space, forming a vast region called the magnetosphere. If you could see it, Jupiter's magnetosphere would appear larger than the Sun in the sky. This magnetic field is generated by the movement of metallic hydrogen deep within Jupiter's interior. The immense pressure inside Jupiter compresses hydrogen to such an extent that it becomes metallic, allowing it to conduct electricity. Jupiter's rapid rotation, it spins once every 10 hours, then generates powerful electric currents within this metallic hydrogen, creating a magnetic field through a process called the dynamo effect. It's similar to how a generator works, but on a planetary scale. Now here's where the symphony begins. Jupiter's magnetic field traps charged particles, electrons and ions, from the solar wind and from Jupiter's own moons, particularly Io, which is volcanically active and constantly spewing sulfur dioxide into space. These charged particles are then accelerated along Jupiter's magnetic field lines, spiraling around them like beads on a string. As these charged particles spiral and accelerate, they emit electromagnetic radiation, including radio waves. This is called synchrotron radiation, and it's the primary source of Jupiter's radio emissions. The faster the particles move and the stronger the magnetic field, the more intense the radio waves. But Jupiter's radio emissions aren't just a uniform hum, they're highly structured and dynamic, varying in frequency, intensity, and polarization. They're like different instruments playing different melodies, creating a complex and ever-changing symphony. One of the most fascinating aspects of Jupiter's radio emissions is that they are not constant. They vary with Jupiter's rotation, with the position of Io, and with solar activity. This tells us that Jupiter's magnetosphere is not a static environment. It's constantly interacting with the solar wind and with its own moons. Io, in particular, plays a crucial role in shaping Jupiter's radio emissions. As Io orbits Jupiter, it interacts with Jupiter's magnetic field, creating powerful electric currents that flow between Jupiter and Io. These currents, known as the Io flux tube, generate intense radio emissions that are easily detectable from Earth. Think of it like this. Io is a giant electrical generator, constantly powering Jupiter's radio symphony. As Io moves through Jupiter's magnetic field, it creates a disturbance like a bow being drawn across a violin string. This disturbance then propagates along Jupiter's magnetic field lines, generating radio waves that travel across vast distances to reach our telescopes. These radio emissions are not just a curiosity. They provide valuable insights into Jupiter's magnetosphere. By studying the frequency, intensity, and polarization of these radio waves, scientists can learn about the strength and structure of Jupiter's magnetic field, the density and energy of the charged particles trapped within the magnetosphere, and the dynamics of the interaction between Jupiter and its moons. In a way, Jupiter's radio emissions are like a planetary heartbeat, revealing the hidden rhythms of this giant world. They're a reminder that what we see is only a small part of the story, and that there's a whole universe of invisible phenomena waiting to be discovered. So next time you look at Jupiter in the night sky, remember that it's not just a beautiful planet of swirling clouds. It's also a powerful radio source, singing a silent symphony that reveals the hidden workings of its magnetic field and the dynamic interplay between Jupiter and its environment. It's a reminder that the universe is full of wonders, even those we can't see with our own eyes. In the next chapter, we'll delve deeper into the mysteries of Jupiter's Great Red Spot, exploring the forces that have kept this colossal storm raging for centuries. We'll see how something that appears so static and unchanging on the surface is actually a dynamic and complex phenomenon driven by the planet's internal heat and rapid rotation. Have you ever gazed into the abyss of a cosmic hurricane? No need for specialized eyewear or a seat on a rocket, though admit it, the latter sounds incredibly cool. Just direct your focus towards Jupiter's most recognizable landmark, the Great Red Spot. It's plastered across countless images, a swirling crimson eye glaring back at us from across the vast expanse of the solar system. But what is it really? What enigmatic secrets are locked within this ancient storm, and why, after all this time, hasn't it dissipated into the Jovian atmosphere? Buckle up, because we're about to plunge headfirst into the swirling heart of Jupiter's most enduring enigma. Forget everything you think you know about Earth hurricanes. While both are undeniably storms, the Great Red Spot operates on a completely different scale, governed by entirely different mechanisms. On Earth, hurricanes are relentlessly fueled by warm ocean water, drawing their immense power from the sea. But Jupiter, it's a gas giant. No oceans to be found, not even a puddle. So what exactly powers this colossal centuries-old storm? What is the secret ingredient that keeps this vortex of fury churning relentlessly? The Great Red Spot is classified as an anticyclonic storm, meaning that unlike cyclones, hurricanes, here on Earth, in the northern hemisphere, it rotates in the opposite direction. Imagine it as a high-pressure system on an astronomical dose of steroids. On Jupiter, this translates into a swirling vortex where the winds reach speeds of over 400 miles per hour. That's faster than any hurricane ever recorded on our own planet. Imagine getting caught in that weather forecast. You wouldn't just lose your umbrella. You'd likely be ripped apart atom by atom and flung into the swirling chaos of the storm itself. Okay, you might be thinking, it's a giant storm, big deal, we have those on Earth. But consider this. The Great Red Spot has been raging for at least 30 years, possibly much longer, its existence predating the invention of the automobile, the light bulb, even the United States itself. We know this because Robert Hooke first described a spot on Jupiter in the 1660s, though there's still debate among historians and astronomers alike whether what Hooke observed was, in fact, the same storm we observe today. Giovanni Cassini definitively described it in 1665, providing detailed observations that leave little doubt about the spot's existence. Regardless, that's centuries of swirling fury, a testament to the sheer power and instability of Jupiter's atmosphere. Earth's hurricanes, by comparison, typically last a few weeks at most, flickering briefly before dissipating. Why such longevity? What allows this Jovian storm to persist for long, seemingly defying the laws of atmospheric physics? That's the million-dollar question, isn't it? Or perhaps, considering the man-hours and resources poured into its study, the billion-dollar question. Scientists are still actively researching the precise mechanisms that sustain the Great Red Spot, meticulously analyzing data from telescopes and probes, building complex computer models, and engaging in heated debates over competing theories. But here's what we know so far. The pieces of the puzzle we've managed to assemble. One key factor is Jupiter's lack of a solid surface. On Earth, hurricanes eventually run out of warm water to fuel them, their energy source cut off, or they make landfall and are disrupted by friction with the ground, their swirling winds slowed and scattered by mountains, forests, and buildings. Jupiter has no such constraints. The storm is free to roam and draw energy from the planet's atmosphere indefinitely, unhindered by any physical barriers. It's a storm unleashed, free to feed and grow without end. But where does that energy come from? This is where things get really interesting, where the story becomes less about established facts and more about educated guesses and ongoing research. One prevailing theory involves the complex interaction of different jet streams within Jupiter's atmosphere. Jupiter's atmosphere is banded with alternating zones of high and low pressure, creating powerful east-west jet streams, like gigantic atmospheric rivers flowing around the planet. The Great Red Spot sits nestled between two of these opposing jet streams, a precarious position that's believed to be crucial to its survival. The interaction between these streams feeds energy into the storm, constantly replenishing its power and keeping it alive. Think of it like a cosmic engine, constantly fueled by the movement of Jupiter's atmospheric currents, perpetual motion machine powered by the planet's own churning atmosphere. Another crucial piece of the puzzle is the role of smaller vortices. Observations have revealed that the Great Red Spot frequently interacts with smaller storms and eddies that drift nearby, swirling around it like moths drawn to a flame. These smaller storms can be absorbed by the Great Red Spot, adding to its energy and contributing to its longevity. It's like a giant bully gobbling up any smaller storms that dare to wander too close, assimilating their power into its own. One could almost imagine the Great Red Spot as a sentient being, actively seeking out and consuming these smaller storms to sustain itself. Now, let's talk about colour. Why is it red? Why isn't it blue, or green, or even a dull grey? That's another mystery that scientists are still trying to unravel, a question that has plagued astronomers for centuries. The leading hypothesis suggests that the red colour is due to complex organic molecules called chromophores that are formed in the upper atmosphere. These molecules are created when ultraviolet radiation from the sun breaks down certain chemicals like ammonia and acetylene in Jupiter's atmosphere. The resulting chromophores absorb blue and green light, reflecting red light back to our eyes, or telescopes, more likely. But where do these chromophores come from, and why are they concentrated in the Great Red Spot? One possibility is that the storm dredges up these chemicals from deeper within Jupiter's atmosphere, bringing them to the surface where they're exposed to sunlight and triggering the formation of chromophores. Another possibility is that the storm itself provides the energy needed to create these molecules, acting as a giant chemical reactor, churning out these colourful compounds in its turbulent heart. Adding another layer of intrigue, the Great Red Spot is shrinking. Observations over the past century have shown that the storm has been steadily decreasing in size, a gradual decline that has sparked concern and speculation among astronomers. In the late 1800s, it was estimated to be large enough to fit 3 Earths inside, a truly colossal storm that dominated Jupiter's southern hemisphere. Now, it's barely big enough for one, a shadow of its former self. Is the Great Red Spot dying? Is it destined to fade away into Jupiter's banded atmosphere, its centuries-long reign coming to an end? No one knows for sure. Some scientists believe that the shrinking is a natural fluctuation, a temporary dip in size that the storm will eventually recover from. They argue that the Great Red Spot has likely undergone similar cycles of expansion and contraction throughout its history, and that this is simply another phase in its long and turbulent life. Others think that it's a sign of its eventual demise, a slow but inevitable decline that will ultimately lead to its disappearance. But even if the Great Red Spot does eventually disappear, it will leave behind a legacy of scientific discovery, a wealth of knowledge gleaned from its study that will continue to inform our understanding of Jupiter and other gas giants for generations to come. Studying this giant storm has taught us a great deal about Jupiter's atmosphere, its dynamics, and the complex interplay of forces that shape the gas giant world. It's a reminder that even the most familiar sights in our solar system can hold profound mysteries, waiting to be unraveled, secrets that challenge our understanding of the universe. So the next time you see a picture of Jupiter with its swirling red eye, remember that you're not just looking at a pretty picture. You're looking at a 3-year-old mystery, a cosmic engine fueled by jet streams and smaller storms, a chemical factory churning out colourful molecules, and a shrinking giant that may one day disappear. You're looking at a testament to the power and complexity of the universe, and a reminder that there's always more to learn, more to discover, more to explore. What's next on our Jupiter journey? We've explored its radio symphony and its iconic Great Red Spot. How about diving deep beneath those swirling clouds to explore what lies beneath? Prepare yourself, because next time we're plunging into the depths of Jupiter's atmosphere, where the pressure crushes anything we know, and the secrets of the planet's formation might just be hiding, waiting to be discovered by those brave enough to venture into the unknown. Ever wondered what it's like to fall forever? Not just the metaphorical existential kind of falling, the slow realization that life is slipping through your fingers. I mean the literal, stomach-churning, never-ending freefall. While that might sound like a philosophical question better suited for a late-night dorm room debate fueled by lukewarm coffee and questionable pizza, on Jupiter, it's a real possibility. A very real and potentially very terrifying possibility. Today we're not just skimming the surface, admiring the pretty stripes like tourists snapping photos. No, we're diving deep, venturing beneath those swirling, colourful clouds to explore the secrets hidden within Jupiter's atmosphere. Forget everything you think you know about planetary surfaces, beaches, mountains, deserts, because what lies beneath is a mind-bending realm of pressure, temperature, and exotic states of matter. Are you ready to take the plunge? Because there's no turning back now. First things first, let's address the elephant in the room, or rather the giant planet in the solar system. Jupiter, unlike Earth, doesn't have a solid surface you could technically land on. You can't plant a flag, build a sandcastle, though ammonia sandcastles might be a thing, or even take a leisurely stroll. Instead, it's a gas giant, primarily composed of hydrogen and helium. So what happens as you descend? What awaits us in the swirling abyss? Imagine yourself strapped into a specialized probe, the Jovian Explorer, a marvel of engineering designed to withstand unimaginable pressures and temperatures. I picture it as a sleek titanium sphere, bristling with sensors and antennae, its surface polished to a mirror sheen to reflect the intense radiation. I can almost feel the hum of the onboard systems, the reassuring thrum of the life support, the faint tang of recycled air. As you pass through the uppermost cloud layers, primarily composed of ammonia crystals, you'd experience increasingly intense winds. Remember those stunning images of Jupiter's bands and zones, the vibrant reds, oranges, yellows, and browns painted across the planet's face? Well, you're now smack dab in the middle of them. These bands are essentially jet streams, roaring around the planet at hundreds of miles per hour. Brace yourselves, a calm, synthesized voice echoes through the probe's interior. Entering the upper atmosphere, turbulence expected. The probe shudders violently. Outside, the swirling ammonia clouds whip past, a blinding white maelstrom. The onboard instruments scream with data, wind speeds exceeding 300 miles per hour, temperatures plummeting to 50 degrees Celsius. The closer you get, the more turbulent your ride becomes. Think of it as the ultimate skydiving experience, only instead of air, you're battling a hurricane of ammonia. It's a chaotic ballet of physics, a dance between the probe's advanced stabilization systems and the raw power of Jupiter's atmosphere. Deeper down, the ammonia clouds give way to clouds of ammonium hydrosulfide, a noxious sulfurous haze that stings the probe's sensors. The colors shift, becoming darker, murkier. Then, finally to water ice clouds. Yes, you read that right, water ice. Even on a planet as seemingly inhospitable as Jupiter, water plays a role. It's a testament to the sheer abundance and versatility of this simple molecule. These layers are crucial because they contribute to the planet's complex weather patterns and energy transport. But don't expect to see any pretty snowflakes. Down here, ice is more like a dense, slushy fog, frigid, swirling soup. As you continue your descent, the pressure and temperature begin to climb dramatically. This is where things get really interesting, and where our understanding becomes a little less clear. The probe's internal temperature starts to rise, the cooling systems working overtime. You're now entering a region where the hydrogen and helium start to transition into a supercritical fluid. What's that, you ask? Good question. It's a question that has puzzled scientists for decades. A supercritical fluid is a state of matter that exists at temperatures and pressures above its critical point, where distinct liquid and gas phases do not exist. Think of it as something in between a liquid and a gas, possessing properties of both. It can flow through solids like a gas, but dissolve materials like a liquid. It's a chameleon of matter, adapting to its extreme environment. In Jupiter's case, this supercritical hydrogen and helium act as a massive, planet-spanning ocean, a sea of unimaginable density and power. Now, imagine the pressure. At these depths, it's hundreds of thousands of times greater than the atmospheric pressure on Earth's surface. The probe creaks and groans under the strain. Internal warning lights flash. To put it in perspective, it's like being at the bottom of Earth's deepest ocean trench, the Mariana Trench, but multiplied by a factor of, well, a lot. Your probe is withstanding forces that would crush a submarine like a tin can. It's a testament to the ingenuity of the engineers who designed it. But even the best engineering has its limits. Pressure levels exceeding expected parameters, the synthesized voice announces, a hint of urgency creeping in, initiating emergency protocols. But the pressure isn't the only thing that's increasing. The temperature is rising too. As you descend further, it climbs to thousands of degrees Celsius. That's hotter than the surface of some stars. The probe's exterior glows red hot, the heat shields working furiously to dissipate the energy. At these temperatures and pressures, the hydrogen starts to undergo another incredible transformation. Here's where things get really wild. Deeper within Jupiter, the immense pressure causes the hydrogen atoms to become so compressed that they lose their electrons. It's like squeezing a sponge until all the water is forced out, only instead of water, it's electrons. This results in a state known as metallic hydrogen. Metallic hydrogen is an exotic phase of hydrogen that conducts electricity like a metal. Scientists have been trying to create it in labs on Earth for decades, but it's incredibly difficult to achieve. It requires pressures and temperatures that are almost impossible to replicate. Jupiter, on the other hand, has vast quantities of it. It's a cosmic laboratory churning out this exotic material on a planetary scale. This metallic hydrogen is thought to play a crucial role in generating Jupiter's powerful magnetic field. Remember that invisible symphony of radio waves we talked about in Chapter 1? Well, the metallic hydrogen swirling within Jupiter's interior is the engine that drives it all. As the planet rotates, the metallic hydrogen generates electric currents, which in turn create a magnetic field that extends millions of miles into space. It's a colossal dynamo operating on a planetary scale, a planetary-sized electrical generator. So how far does this metallic hydrogen layer extend? That's one of the big questions scientists are still trying to answer. It's believed to make up a significant portion of Jupiter's interior, possibly extending halfway to the planet's center. Imagine a sphere of liquid metal, swirling and churning, generating a magnetic field that protects the entire planet from the solar wind. It's a truly awe-inspiring concept. And what about that center? What lies at the heart of Jupiter? This is where things get even more speculative. While Jupiter is primarily composed of hydrogen and helium, scientists believe it may have a dense core made of heavier elements, like rock and metal. This core is thought to be relatively small, perhaps only a few times the size of Earth, but it's incredibly dense, packing a huge amount of mass into a small space. It's like a cosmic anchor holding the entire planet together. The existence and composition of this core are still debated. Some scientists believe it's a solid rocky object, a remnant of the planet's formation. Others think it might be more of a fuzzy, ill-defined region, where the heavier elements are mixed with metallic hydrogen. It could be a slushy mix of rock, metal, and exotic hydrogen compounds. Determining the nature of Jupiter's core is one of the key goals of ongoing and future missions to the planet. It's like trying to solve a cosmic puzzle, with each new piece of data bringing us closer to the truth. Think about the implications for a moment. If Jupiter does have a solid core, it would suggest that the planet formed in a similar way to the terrestrial planets, like Earth and Mars, by accreting planetesimals. It would support the core accretion model of planetary formation. On the other hand, if Jupiter lacks a solid core, it would support the idea that it formed directly from the collapse of a protoplanetary disk. This is known as the disk instability model. Understanding Jupiter's core is therefore crucial for understanding how our solar system, and potentially other planetary systems, formed. It's a window into the past, a glimpse at the very beginnings of our cosmic neighbourhood. Our journey beneath Jupiter's clouds has revealed a world far stranger and more complex than we could have imagined. From the turbulent cloud layers to the exotic realm of metallic hydrogen and the mysterious core, Jupiter's interior is a frontier of scientific discovery. While we may not be able to physically travel to these depths anytime soon, robotic probes and sophisticated computer models are helping us piece together the puzzle. Each new discovery brings us closer to understanding the secrets of this gas giant. "Probe integrity compromised," the synthesized voice announces, its tone now laced with alarm. "Mission parameters exceeded. Initiating emergency ascent." So, what have we learned? We've learned that Jupiter is not just a giant ball of gas, but a dynamic, evolving world with a hidden interior. We've learned that pressure and temperature can transform matter into exotic states that defy our everyday experience. And we've learned that there's still so much more to discover about this fascinating planet. The universe is full of surprises, and Jupiter is just one example of its boundless creativity. But the exploration doesn't stop here. In our next chapter, we'll be venturing even further afield, leaving Jupiter behind to explore its fascinating family of moons. From volcanic Io to icy Europa, Jupiter's moons are worlds in their own right, each with its own unique story to tell. Are you ready for another adventure? Because the cosmos is vast and there's a whole universe waiting to be explored. So you've plunged through Jupiter's dizzying atmosphere, felt the bone-crushing pressure of supercritical hydrogen, and maybe even caught a fleeting glimpse of the elusive core in your mind's eye. But hold on tighter than you think you can. The real weirdness, the truly mind-bending stuff, is just beginning. Forget everything you think you know about rain. On Jupiter, it might just be diamonds. And forget peaceful blue oceans reflecting a warm sun. Here, they could be swirling seas of liquid helium, a substance that boils away instantly on Earth. Sound like science fiction ripped from the pages of a pulpy novel? Buckle up, Buttercup. This is Jupiter, and reality here outstrips even the wildest imagination. Ever wonder what happens deeper down, where the pressure becomes truly unimaginable, the kind that would turn steel into putty? You know how we talked about metallic hydrogen, that bizarre state of matter, where hydrogen atoms are squeezed so tightly that they share their electrons, transforming the gas into an electrically conductive fluid, like some cosmic superconductor? Well, that's just the tip of the iceberg, or rather, the tip of the gas giant, a mere ripple on the surface of a truly alien sea. Think about this for a moment. Really think about it. The immense pressure, a force so profound it reshapes the very nature of matter, isn't just affecting hydrogen. It's squeezing everything. Every single atom, every molecule is subjected to this unimaginable force. And what happens when you squeeze carbon atoms, the very building blocks of life as we know it, under tremendous, crushing pressure? You get diamonds, of course. Brilliant, glittering, incredibly hard diamonds. Now, this isn't exactly a universally accepted theory etched in stone and proclaimed from the mountaintops. It's a hypothesis, a bold, audacious idea based on our understanding of physics and chemistry under extreme conditions. But the logic, the sheer elegance of the idea is compelling. Jupiter's atmosphere, in its swirling, chaotic beauty, contains methane, CH4, a simple molecule of carbon and hydrogen. As you descend, plunging deeper into the planet's embrace, increasing pressure and temperature could break down these methane molecules, tearing them apart like toys in the hands of a cosmic giant. The freed carbon atoms, stripped from their hydrogen bonds and subjected to that immense pressure, could then form into larger and larger structures, bonding with each other, eventually crystallizing into diamonds. Imagine it, diamond rain. Not a gentle drizzle, a soft romantic shower of glittering stones, like something out of a fairy tale, mind you, but a torrential, deafening downpour of glittering stones, each one potentially larger than your fist. Some perhaps the size of boulders tumbling through the atmosphere. These diamonds, formed in the upper layers of Jupiter's atmosphere, would then fall through the metallic hydrogen layer, deeper and deeper into the planet, a glittering cascade into the unknown, a cosmic river of gems. What happens to them then? That's where things get even more speculative, more akin to crafting a plausible narrative than stating established fact, but also incredibly interesting. Some scientists, the boldest dreamers among us, theorized that these diamonds might eventually sink all the way to Jupiter's core, forming a diamond layer around it, a glittering shell encasing the planet's heart. Others proposed that the diamonds might melt, or rather dissolve, into the metallic hydrogen at even deeper, hotter levels, becoming part of the planet's very fabric. Imagine, Dr. Ashes Thorne, a planetary scientist at Caltech, mused during a lecture, his eyes twinkling with excitement. A diamond the size of Everest slowly sinking through liquid metallic hydrogen. The sheer scale of it is breathtaking. Is there any way to prove this? To actually see this diamond rain? To witness the birth of a diamond ocean? Well, sending a probe deep enough to actually witness diamond rain is, shall we say, a challenge. A monumental, near impossible challenge. The pressure and temperature at those depths would crush any spacecraft we can currently build, turning it into a mangled mess of metal and circuits in mere seconds. It's like trying to send a paper boat to the bottom of the Mariana Trench. However, scientists, ever resourceful, are working on indirect methods, clever ways to peek inside Jupiter without actually going there. One approach involves studying Jupiter's magnetic field. Remember how we talked about metallic hydrogen being electrically conductive? The movement of this metallic hydrogen, swirling and churning within the planet, generates Jupiter's powerful magnetic field, a force field that extends for millions of kilometers into space. If there's a layer of diamonds around the core, or even a change in the composition of the metallic hydrogen due to dissolved carbon, it could subtly affect the magnetic field, creating tiny anomalies, minute variations that could betray the presence of these hidden treasures. Sophisticated analysis of Jupiter's magnetic field anomalies using data from missions like Juno, which is currently orbiting Jupiter and meticulously mapping its magnetic field, might provide clues about the presence and distribution of diamonds deep inside the planet. It's like listening to a heartbeat, explained Alina Hansen, a Juno mission scientist. We can't see the heart directly, but we can analyze the rhythm, the strength, and any irregularities to learn about its condition. Another avenue of research involves laboratory experiments. Scientists are trying to recreate the extreme pressures and temperatures found inside Jupiter using powerful diamond anvil cells. These devices, technological marvels in their own right, can squeeze tiny samples of materials to pressures exceeding those found at the center of the Earth. By studying how methane and other carbon-containing compounds behave under these conditions, observing their transformations and measuring their properties, we can gain a better understanding of the potential for diamond formation inside Jupiter. Think of it like this. You're a detective trying to solve a crime. You can't directly observe the crime scene, the hidden depths of Jupiter, but you can gather clues, magnetic field data, lab experiments, and use your knowledge of physics and chemistry to piece together what might be happening deep inside Jupiter. You analyze the evidence, build a case, and present your findings to the scientific community, hoping to convince your peers that your theory holds water. But diamonds aren't the only surprise lurking within Jupiter's depths. Remember helium, the second most abundant element in Jupiter's atmosphere? It too behaves in peculiar ways under extreme pressure and temperature, defying our earthly intuition. Under normal conditions here on Earth, helium and hydrogen mix readily, forming a homogeneous gas. But inside Jupiter, things are anything but normal. As you descend deeper and the pressure increases, helium starts to separate from the hydrogen, like oil and water refusing to mix. This is because helium, being heavier than hydrogen, becomes less soluble in metallic hydrogen at high pressures. It's a subtle difference in density, but under immense pressure it becomes a driving force. Imagine mixing oil and water in a jar. They might initially seem to blend, creating a cloudy mixture, but eventually they separate into distinct layers, the oil floating on top of the water. Something similar is happening inside Jupiter, but with helium and metallic hydrogen on a planetary scale. So what happens to the separated helium? Well, scientists believe it forms droplets. Think of them as tiny balloons of liquid helium that then fall through the metallic hydrogen layer, like miniature submarines diving into an alien ocean. This helium rain, unlike the diamond rain, is thought to release heat as it falls, a gentle warming effect that permeates the planet's interior. This heat could play a significant role in Jupiter's internal dynamics, potentially influencing the planet's temperature profile and atmospheric circulation, driving the powerful winds and swirling storms that we observe from afar. And here's where it gets really wild, where the boundaries between science and science fiction blur. As these helium droplets fall, they might coalesce into larger and larger pools, merging together like raindrops forming a puddle, eventually forming vast planet-encircling oceans of liquid helium deep within Jupiter. Picture this. You're floating in a hypothetical ultra-advanced submarine, constructed from materials yet to be invented, descending through the metallic hydrogen layer. The pressure is immense, the temperature scorching, but your vessel holds firm. Suddenly, you break through a hazy boundary, a shimmering interface, and find yourself in a seemingly endless ocean of shimmering superfluid helium. It's a landscape unlike anything you could imagine, a testament to the bizarre physics that governs the interiors of gas giants. A vast, silent ocean of liquid cold stretching to the horizon in every direction. Again, we can't directly observe these helium oceans, but scientists have developed sophisticated computer models, complex simulations that run on the world's most powerful supercomputers that simulate the behavior of hydrogen and helium under extreme conditions. These models predict the separation of helium and the formation of helium rain, providing strong evidence for the existence of these hidden oceans. The models aren't perfect, of course, but they are constantly being refined and improved, bringing us closer to understanding the truth about Jupiter's interior. Furthermore, the helium rain theory helps explain a long-standing puzzle about Jupiter, its surprisingly low abundance of neon in the upper atmosphere. Neon is highly soluble in liquid helium, like sugar dissolving in water. So as the helium rain falls, it could be dragging neon from the upper atmosphere down into the planet's interior, effectively depleting the upper atmosphere of this element. This explanation is consistent with observations from the Galileo probe, which plunged into Jupiter's atmosphere in 1995 and found significantly less neon than expected. It's like a cosmic vacuum cleaner, sucking up neon and depositing it deep within the planet. What does all this mean? It means that Jupiter isn't just a big ball of gas, a featureless sphere in the night sky. It's a dynamic, complex world with hidden layers, exotic forms of matter, and processes that we are only beginning to understand. Diamond rain, helium oceans. These aren't just fanciful ideas, the musings of eccentric scientists. They are testable hypotheses based on sound scientific principles that are pushing the boundaries of our knowledge about planetary interiors. They represent the cutting edge of planetary science, the quest to unravel the mysteries of the cosmos, and the implications extend far beyond Jupiter. By studying Jupiter, we can gain insights into the formation and evolution of other gas giants, both in our own solar system and around other stars. Understanding how these planets work can help us understand the diversity of planetary systems throughout the galaxy, and potentially even shed light on the conditions necessary for the formation of habitable planets. Jupiter, in its alien beauty, might hold the key to understanding our place in the universe. So the next time you look up at Jupiter in the night sky, remember that you're not just seeing a giant ball of gas. You're seeing a world of hidden wonders, a world of diamond rain and helium oceans, a world that continues to challenge and inspire our scientific curiosity. A world that reminds us that the universe is far stranger, far more wondrous than we could ever have imagined. What other secrets is Jupiter hiding? Only time and continued exploration will tell. The quest continues. Ever looked up at Jupiter and noticed those pinpricks of light dancing around it? You probably know they're moons, but did you ever stop to wonder if they were just there? Just inert rocks orbiting a giant? Think again. Jupiter's moons are a whole solar system unto themselves, each a unique world with secrets that can rewrite our understanding of, well, everything. We're not just talking about any moons here. We're talking about moons with subsurface oceans, active volcanoes, and potential for, well, let's not get ahead of ourselves. But let's just say that these aren't your average, run-of-the-mill lunar landscapes. Let's start with the big guys, the Galilean moons. These four, Io, Europa, Ganymede, and Callisto, were the first celestial objects discovered to orbit a planet other than Earth, thanks to Galileo Galilei's groundbreaking observations in 1610, and they've been blowing our minds ever since. First up, Io. Imagine a world constantly being pummeled by volcanic eruptions. Not just little, gentle puffs of smoke, but colossal plumes of sulfurous material blasting hundreds of miles into space. That's Io. Why all the volcanic activity? Well, it's all about tidal forces. Jupiter's immense gravity, along with the gravitational tugs of Europa and Ganymede in a complex orbital dance called a Laplace resonance, constantly kneads and flexes Io. This generates immense heat within the moon's interior, leading to the most volcanically active world in our solar system. Think of it like squeezing a stress ball repeatedly. All that squeezing generates heat, right? Io is the ultimate cosmic stress ball. The volcanoes spew out sulfur and sulfur dioxide, giving Io its characteristic mottled appearance. A bizarre landscape of yellows, oranges, reds, and browns. Forget tranquil seas and rolling hills. Io is a world of fire and brimstone. Is it beautiful, in a terrifying, awe-inspiring way? Absolutely. Would you want to vacation there? Probably not, unless you're really into extreme tourism. Now, let's hop over to Europa. In stark contrast to Io's fiery hellscape, Europa presents a serene, almost pristine surface of ice. But don't let appearances fool you. Beneath that icy shell lies a global ocean of liquid water, potentially twice the volume of all Earth's oceans combined. How do we know there's an ocean? Several lines of evidence point to it. First, Europa has a very smooth surface with few craters, suggesting that it's constantly being resurfaced by liquid water welling up from below. Second, measurements of Europa's magnetic field indicate the presence of a conductive layer, like salty water, beneath the ice. And third, observations of plumes of water vapour erupting from Europa's south pole provide tantalising glimpses of what lies beneath. Think of Europa like a cosmic ice cube with a hidden surprise inside. The big question, of course, is, what's in that ocean? Could it harbour life? The conditions are certainly intriguing. Europa's ocean is thought to be in contact with a rocky mantle, providing a potential source of chemical energy. Hydrothermal vents, similar to those found on Earth's ocean floor, could be spewing out minerals and nutrients, creating oases for life. It's a long shot, sure, but the possibility of finding life on Europa is one of the most exciting prospects in modern science. Are we alone? Europa might just hold the answer. Next up, Ganymede, the largest moon in the solar system, bigger than the planet Mercury. Ganymede is unique for another reason. It's the only moon in the solar system known to have its own magnetic field. This magnetic field is likely generated by a dynamo effect within a liquid iron core, similar to how Earth's magnetic field is generated. But here's where it gets really interesting. Ganymede, like Europa, is believed to have a subsurface ocean. In fact, it might have multiple layers of ice and water stacked on top of each other, like a bizarre cosmic club sandwich. This complex internal structure is still not fully understood, but it suggests that Ganymede is a far more dynamic and geologically active world than previously thought. Imagine peeling back the layers of Ganymede, like an onion, revealing a series of icy shells and hidden oceans. What secrets are hidden within those depths? What forces shape Ganymede's magnetic field? These are questions that scientists are actively trying to answer. Finally, we have Callisto, the outermost of the Galilean moons. Callisto is the most heavily cratered object in the solar system, a testament to its ancient surface. Unlike the other Galilean moons, Callisto doesn't seem to have a subsurface ocean, or at least not a very significant one. It's a relatively quiet and geologically inactive world, but even Callisto has its mysteries. Measurements of its magnetic field suggest that it may have a layer of salty water deep beneath its surface, although it's much less pronounced than the oceans of Europa and Ganymede. Why is Callisto so different from its siblings? Why didn't it undergo the same tidal heating and geological activity? These are questions that continue to puzzle scientists. What's the big takeaway here? Jupiter's moons are not just inert rocks orbiting a giant planet. They are complex, dynamic worlds with hidden oceans, active volcanoes, and the potential to revolutionize our understanding of life in the universe. Each moon tells a unique story, a story of tidal forces, geological activity, and the search for habitable environments beyond Earth. But the Galilean moons aren't the only players in Jupiter's lunar system. Jupiter has dozens of other moons, ranging in size from tiny asteroids to relatively large, irregularly shaped objects. These moons are divided into several groups, based on their orbital characteristics. Many of these moons are thought to be captured asteroids, remnants from the early solar system that were gravitationally snagged by Jupiter's immense gravity. They orbit Jupiter in highly elliptical and inclined orbits, often moving in the opposite direction to Jupiter's rotation, retrograde orbits. These smaller moons may not be as glamorous as the Galilean moons, but they provide valuable clues about the formation and evolution of the solar system. By studying their composition and orbital characteristics, we can learn more about the building blocks of planets and the processes that shape the early solar system. Think of Jupiter's smaller moons as cosmic time capsules, preserving information about the early days of our solar system. What secrets do they hold? What can they tell us about the origin of Jupiter and the other planets? The exploration of Jupiter's moons is far from over. Future missions, such as the European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, and NASA's Europa Clipper mission, will delve deeper into the mysteries of these fascinating worlds. These missions will carry advanced instruments to probe the subsurface oceans, map the surfaces in unprecedented detail, and search for signs of life. What will we find? Will we discover evidence of life on Europa? Will we unravel the secrets of Ganymede's magnetic field? Will we learn more about the origin of Jupiter's smaller moons? Only time will tell. But one thing is certain. The exploration of Jupiter's moons promises to be one of the most exciting and rewarding scientific endeavours of the 21st century. So the next time you look up at Jupiter and see those tiny pinpricks of light, remember that you're not just looking at moons, you're looking at worlds, each with its own unique story to tell. You're looking at potential habitats for life, at clues to the origin of our solar system, and at the boundless wonders of the universe. You're looking at a whole lot more than they taught you in school. Aren't you glad you know better now? Ever look up at Jupiter, that behemoth of a planet dominating the night sky, and think, wow, that's a big planet? You're not wrong, of course, it's a statement of the obvious. But what if I told you there's more to Jupiter's grandeur than just its swirling clouds, the great red spot, and its colossal size? What if I told you it has rings? Wait, rings? Like Saturn? The image that probably sprang to mind is a dazzling halo of ice, a celestial crown fit for a king. Well, yes, but different. Picture this, Saturn, the flamboyant showman strutting across the cosmic stage with its rings shimmering like a million diamonds. Saturn hogs the ring spotlight, and rightfully so. Its rings are spectacular, dazzling, a breathtaking vista composed of icy chunks that reflect sunlight like a cosmic disco ball. A swirling, glittering extravaganza. Jupiter's rings, on the other hand, are more like a shy, retiring cousin who prefers to hang out in the shadows, sipping tea and reading poetry in a dimly lit corner. They're faint, dusty, and easily overlooked, a subtle whisper compared to Saturn's booming declaration. I remember the first time I saw a detailed image of Jupiter's rings. I was a graduate student poring over data from the Galileo probe. I almost missed them. They were so faint, so diffuse, that they barely registered against the background noise of space. But then, as I adjusted the contrast and sharpened the image, they began to emerge like a secret being revealed. It was a moment of quiet awe, but don't let their subtlety fool you. These rings tell a story of impacts, moons, and the ever-present gravitational dance that defines the Jovian system. They are a testament to the constant activity and dynamic processes that shape our solar system. They are a map of collisions and gravitational interactions etched in dust and light. So what makes Jupiter's ring so different from Saturn's magnificent spectacle? And what secrets to hold, hidden within their faint glow? Let's dive in, shall we? Grab your metaphorical spacesuit, and let's explore this often overlooked wonder of the Jovian system. First off, composition. While Saturn's rings are primarily made of ice, gleaming white and pristine, Jupiter's are composed mainly of dust. Think tiny particles, about the size of smoke particles, constantly being replenished. Imagine the fine dust that settles on your furniture. Only these particles are orbiting a giant planet millions of miles away. Where does all this dust come from? That's where Jupiter's inner moons come into play. the unsung heroes of Jupiter's ring system. Specifically, we're talking about Métis, Adrastea, Amalthea, and Thebe. These small, irregularly shaped moons, more like lumpy potatoes than celestial spheres, orbit within Jupiter's ring system. They are constantly bombarded by micrometeoroids, tiny space rocks, remnants from the formation of the solar system, zipping around the Jovian system at incredible speeds. These impacts kick up dust particles, like a cosmic sandblaster at work, which then become trapped in Jupiter's gravitational field, forming the rings. It's like a cosmic game of pinball, with the moons as the bumpers and the micrometeoroids as the ball. Each impact sends a shower of dust into orbit, contributing to the overall structure of the rings. I picture these moons as weary travellers, perpetually peppered by space dust, their surfaces scarred and cratered from eons of bombardment. They are the silent guardians of Jupiter's rings, constantly sacrificing themselves to maintain this delicate structure. Now, let's talk structure. Jupiter's ring system isn't one solid band like a vinyl record, perfectly smooth and uniform. Instead, it's made up of several distinct components, each with its own characteristics and origin, a complex tapestry woven from dust and gravity. You have the main ring, which is the brightest and densest part of the system, though still incredibly faint compared to Saturn's rings. It extends from about 92,000 kilometers to 120,500 kilometers from Jupiter's center. This ring is primarily composed of dust ejected from Métis and Adrastea. The sharp outer edge of the main ring is maintained by Adrastea, acting as a shepherd moon, gravitationally confining the dust particles. Imagine a cosmic sheepdog herding its flock, nipping at the heels of stray particles, keeping the dust in line and preventing it from dispersing. Adrastea's influence is crucial in maintaining the integrity of the main ring. Then there's the halo ring, which is a fainter, more diffuse structure that extends inward from the main ring towards Jupiter. It's made up of even smaller dust particles than the main ring, likely originating from the same sources but spread out by electromagnetic forces. The halo is like a faint, ethereal glow surrounding the planet, almost invisible to the naked eye, a subtle aura that adds to Jupiter's mystique. It's a testament to the power of electromagnetic forces, shaping the dust into a delicate, almost ghostly form. Beyond the main ring, you have the gossamer rings. These are even fainter and more tenuous than the halo, extending outward as to the orbits of Amalthea and Thebe. As you might guess, they're named gossamer because of their delicate, almost transparent appearance, like spun silk stretched across the vastness of space. These rings are composed of dust ejected from Amalthea and Thebe, respectively. Each moon has its own gossamer ring, creating two distinct yet overlapping structures. Imagine two faint halos, intertwined and overlapping, a subtle dance of dust and gravity. So you've got this constant cycle of dust being kicked up from the inner moons and then gradually spiraling inward towards Jupiter due to various forces, including radiation pressure and electromagnetic drag. The sunlight itself, gentle as it seems, exerts a pressure on these tiny particles, pushing them inwards. This means that Jupiter's rings are relatively short-lived compared to Saturn's. They're constantly being replenished, a dynamic and ever-changing system, a cosmic recycling program in action. It's a reminder that nothing in space is static. Everything is in constant motion, constantly evolving. But wait, there's more. Remember Jupiter's powerful magnetic field we talked about earlier? Well, it plays a crucial role in shaping the rings, especially the halo. The tiny dust particles in the halo are electrically charged, and Jupiter's magnetic field interacts with these charged particles, causing them to spread out and form the diffuse halo structure. It's like a cosmic paintbrush, using magnetic forces to create a delicate ethereal artwork. Imagine the magnetic field lines as invisible brush strokes, guiding the charged dust particles into their ethereal formation. Now you might be asking, why are Jupiter's rings so much fainter than Saturn's? That's a great question. The answer lies in the composition and size of the particles. Saturn's rings are made of larger, icy particles that reflect sunlight much more efficiently. Jupiter's rings, on the other hand, are made of smaller, darker dust particles that don't reflect light as well. Think of it like comparing a snow-covered field to a dusty parking lot. The snow reflects sunlight brilliantly, creating a dazzling spectacle, while the dust absorbs it, appearing dull and unremarkable. Another factor is the gravitational environment. Jupiter's gravity is much stronger than Saturn's, which means that dust particles are more easily pulled towards the planet. This makes it harder for them to accumulate and form dense, bright rings. It's like trying to build a sandcastle on a beach with strong tides. The waves constantly wash away the sand, preventing the castle from reaching its full potential. Okay, so we've established that Jupiter's rings are faint, dusty, and constantly being replenished. But what does studying them tell us about Jupiter and its environment? Why should we care about these faint, almost invisible structures? Well, for starters, they provide valuable insights into the impact rates in the Jovian system. By studying the size and distribution of dust particles in the rings, scientists can estimate how often the inner moons are being bombarded by micrometeoroids. This in turn can help us understand the overall population of small objects in the outer solar system. It's like reading the rings as a historical record of collisions, a chronicle of impacts written in dust. Furthermore, the rings can act as a sort of detector for unseen moons or other objects orbiting near Jupiter. If a small moon were to pass through the rings, it would create disturbances in the dust distribution, which could be detected by spacecraft. It's like a cosmic tripwire, alerting us to the presence of hidden objects, revealing secrets lurking in the shadows. The rings also give us clues about the composition and properties of the inner moons. By analysing the dust particles in the rings, scientists can infer the composition of the materials that make up Metis, Adrastea, Amalthea, and Thebe. It's like analysing the crumbs to figure out what kind of cake was baked, piecing together the puzzle of the moon's composition from the dust they shed. Finally, studying the interaction between the rings and Jupiter's magnetic field can help us understand the complex electromagnetic environment around the planet. The rings act as a sort of tracer, allowing us to visualize the magnetic field lines and study the behavior of charged particles. It's like using the rings as a cosmic weather vane, revealing the invisible forces that shape the environment around Jupiter. So while Jupiter's rings may not be as flashy as Saturn's, they are a valuable source of scientific information. They're a dynamic and ever-changing system, constantly being shaped by impacts, moons, and Jupiter's powerful gravitational and magnetic forces. They are a window into the complex and dynamic processes that shape the Jovian system. Future missions to Jupiter, like the JUICE, Jupiter Icy Moons Explorer mission, may carry instruments capable of studying the rings in even greater detail. These observations could provide new insights into the origin, evolution, and composition of the rings, as well as the processes that shape the Jovian system as a whole. Who knows what secrets are still hidden within those faint, dusty bands? What new discoveries await us, hidden within the subtle glow of Jupiter's rings? Think about it. These rings, born from countless tiny impacts, are a testament to the chaotic beauty of space. They're a reminder that even the most subtle features can hold profound scientific significance. So the next time you gaze up at Jupiter, remember that there's more to this gas giant than meets the eye. Beneath those swirling clouds and within its powerful magnetic field lies a delicate ring system, whispering secrets of impacts, moons, and the intricate dance of gravity. Are you listening? Can you hear the faint whisper of the rings, telling their story of dust and gravity? Ever stop and truly wonder about Jupiter? Beyond the swirling colours and iconic great red spot, does that colossal gas giant harbour secrets, a role far grander than simply orbiting the Sun? What if Jupiter is more than just a giant ball of gas and swirling storms? What if it's playing a role far beyond its own orbit, a silent guardian of our inner solar system? Buckle up, because we're about to explore Jupiter's surprising influence as the solar system's protector and sculptor, a cosmic bouncer with a gravity that shapes the destinies of asteroids and comets alike. You see, Jupiter's immense gravity acts as a kind of cosmic bouncer, deflecting and capturing asteroids and comets that might otherwise wreak havoc closer to home. Think of it as a planetary goalie, constantly guarding the inner solar system from potentially devastating impacts. But how effective is this cosmic defense system, and what are the trade-offs? Is Jupiter truly a benevolent protector, or does its gravitational influence sometimes backfire, sending icy missiles hurtling toward Earth? These are the questions that keep planetary scientists up at night, staring at simulations and crunching numbers, trying to understand the delicate balance of our solar system. Let's start with the basics. Jupiter's gravity is so strong, more than twice the combined gravity of all the other planets in the solar system, that it significantly perturbs the orbits of smaller bodies. This gravitational influence can manifest in a couple of key ways. Imagine the sheer power, the invisible force constantly emanating from this giant, subtly altering the paths of everything that wanders too close. First, Jupiter can act as a shield. Imagine a stream of comets hurtling inward from the outer solar system, icy remnants from the formation of our Sun and planets. These comets, driven by the gravitational pull of the Sun, represent a constant threat to the inner planets. As these icy wanderers approach Jupiter, its gravity can deflect them, flinging them out of the solar system altogether, or altering their trajectories so they never cross Earth's orbit. This gravitational scattering is a crucial mechanism in protecting the inner planets. It's like a cosmic shield, deflecting potentially devastating blows. Dr. Aris Thorne, a leading astrophysicist at Caltech, once described it as, "Jupiter is the solar system's first line of defense. Without it, the inner planets would be subjected to a far greater frequency of impacts." But here's the twist. Jupiter can also act as a slingshot. Sometimes, instead of deflecting comets away, Jupiter's gravity can accelerate them and redirect them inward, toward the inner solar system. This is where things get a little more complicated, where the benevolent protector becomes a potential threat. It's a cosmic paradox. Think of it like a cosmic game of billiards. A comet approaching Jupiter at just the right angle and speed can receive a gravitational kick, sending it careening towards the inner solar system at increased velocity. This process can significantly increase the risk of impacts on Earth and other inner planets. Imagine the comet, initially drifting harmlessly through the outer solar system, suddenly caught in Jupiter's gravitational web. It spirals closer and closer, gathering speed, until, with a final gravitational push, it's flung inward, a potentially deadly projectile aimed at the heart of the solar system. So, is Jupiter a protector or a threat? The answer, as you might expect, is both. It's a complex interplay of gravitational forces that shapes the distribution of asteroids and comets throughout the solar system. It's a delicate dance of attraction and repulsion, a constant balancing act that determines the fate of these celestial wanderers. Now, Let's delve into the evidence. One of the most dramatic examples of Jupiter's influence came in 1924, with the spectacular collision of comet Shoemaker-Levy 9. This comet had been captured by Jupiter's gravity and broken apart into numerous fragments. Over several days, these fragments slammed into Jupiter's southern hemisphere, creating massive dark scars in the planet's atmosphere that persisted for months. I remember watching the news reports my younger self, mesmerized by the images. The dark splotches on Jupiter's surface were a stark reminder of the raw power of the cosmos and the potential for catastrophic impacts. It was a wake-up call, Professor Evelyn Reed, a planetary geologist, told me in an interview. Shoemaker-Levy 9 showed us in no uncertain terms that these events are not just theoretical possibilities. They can happen, and they can have devastating consequences. This event served as a stark reminder of the potential for catastrophic impacts in our solar system, and highlighted Jupiter's role in intercepting such objects. Imagine if those comet fragments had been on a collision course with Earth. The devastation would have been unimaginable, but the story doesn't end there. Scientists have also discovered families of asteroids that are gravitationally shepherded by Jupiter. These asteroids, known as the Trojan asteroids, orbit the Sun at the same distance as Jupiter, clustered around two stable points called Lagrange points, located 60 degrees ahead of and behind Jupiter in its orbit. They are named after heroes of the Trojan War, adding a touch of mythology to the science. These Trojan asteroids are like cosmic stowaways trapped in Jupiter's gravitational embrace. They provide valuable insights into the early solar system, as they are believed to be remnants of the primordial building blocks that formed the planets. Studying their composition and distribution can tell us a lot about the conditions that existed in the solar system billions of years ago. It's like looking back in time, examining the fossilized remnants of the solar system's infancy. Furthermore, Jupiter's gravity has likely played a significant role in shaping the asteroid belt, located between Mars and Jupiter. It's believed that Jupiter's gravitational perturbations prevented the asteroids in this region from coalescing into a planet. Instead, they remain as a collection of rocky fragments, constantly colliding and interacting with each other. The asteroid belt, a chaotic jumble of space rocks, is a testament to Jupiter's disruptive influence. Could a planet have formed in the asteroid belt if Jupiter wasn't there? It's a fascinating question that scientists continue to explore. Simulations suggest that without Jupiter's influence, the asteroid belt could have potentially coalesced into a planet several times the size of Earth. Imagine another Earth-sized planet orbiting the Sun, nestled between Mars and Jupiter. How would that have changed the dynamics of the solar system? Would life have evolved there? These are the what-ifs that fuel scientific inquiry. Now let's consider the implications for life on Earth. Some scientists argue that Jupiter's protective role has been crucial for the development of life on our planet. By deflecting or capturing potentially hazardous asteroids and comets, Jupiter has reduced the frequency of catastrophic impacts, creating a more stable environment for life to evolve. It's a comforting thought that this giant planet is looking out for us, shielding us from cosmic dangers. But others argue that Jupiter's influence may have also had negative consequences. By occasionally redirecting comets inward, Jupiter may have contributed to periods of intense bombardment in the early solar system, potentially hindering the development of life on Earth. It's a double-edged sword, this gravitational influence. It's a complex and ongoing debate, but one thing is clear. Jupiter's gravity has had a profound impact on the evolution of our solar system and the conditions that have allowed life to flourish on Earth. The story of life on Earth is inextricably linked to the gravitational dance of Jupiter and the smaller bodies that populate our solar system. So the next time you look up at the night sky and see Jupiter shining brightly, remember that it's more than just a beautiful planet. It's a cosmic guardian, a gravitational sculptor, and a key player in the ongoing story of our solar system. And just like any good bouncer, sometimes it lets a few through. No system is perfect. But what about the future? As we continue to explore our solar system, how will our understanding of Jupiter's influence evolve? Will we discover new ways in which Jupiter protects or threatens the inner planets? And could we potentially harness Jupiter's gravity for our own purposes, perhaps to deflect asteroids that pose a threat to Earth? The possibilities are endless. Imagine a future where we can predict and even manipulate the paths of asteroids and comets, using our understanding of Jupiter's gravity to safeguard our planet. These are just some of the questions that scientists are grappling with as they continue to study Jupiter and its role in the solar system. As technology advances and we send more spacecraft to explore this giant planet, we're sure to uncover even more surprise about its complex and fascinating influence. Each new mission brings us closer to understanding the mysteries of Jupiter and its role in the grand cosmic scheme. Think about the possibilities. Could we one day develop a system to actively manage Jupiter's gravitational influence, perhaps using strategically placed spacecraft to nudge asteroids and comets onto safer trajectories? It sounds like science fiction, but with enough ingenuity and technological advancement, it might just be possible. Perhaps we could even use Jupiter's gravity to slingshot spacecraft to distant stars, unlocking the secrets of the galaxy. For now, we can continue to marvel at Jupiter's power and complexity, appreciating its crucial role in shaping our solar system and protecting our planet. It's a reminder that even the seemingly distant and remote corners of the universe can have a profound impact on our lives. So next time you gaze at Jupiter, remember it's not just a giant, but a sentinel, a guardian, a silent protector working tirelessly to keep our corner of the cosmos a little bit safer. Isn't space just amazing? The sheer scale of it all, the intricate dance of gravity and motion, the endless possibilities for discovery. It's enough to make you feel both insignificant and incredibly fortunate to be a part of it all. Ever seen the northern lights dance across the sky on a crisp winter night? It's breathtaking, isn't it? But what if I told you Jupiter puts on an even more spectacular light show? One so powerful it makes Earth's auroras look like a flickering candle next to a stadium spotlight. You might think I'm exaggerating, but trust me, when it comes to auroras, Jupiter is in a league of its own. So what makes Jupiter's auroras so extraordinary? Let's dive in and uncover the secrets behind this celestial spectacle. First, let's recap the basics. Auroras, whether on Earth or Jupiter, are caused by charged particles interacting with a planet's magnetic field and atmosphere. On Earth, these particles primarily come from the Sun in the form of solar wind. These particles are funneled along the Earth's magnetic field lines towards the poles, where they collide with atmospheric gases like oxygen and nitrogen. These collisions excite the gas molecules, causing them to emit light of various colours, greens, reds, blues and purples we see in the aurora borealis and australis. Now, Jupiter has a similar process, but with a few crucial twists that amplify the whole phenomenon to a mind-boggling scale. Remember how we discussed Jupiter's ridiculously powerful magnetic field in Chapter 1? It's about 20,000 times stronger than Earth's. This colossal magnetic field is the first key ingredient in Jupiter's aurora recipe. But the Sun isn't the only source of particles fueling Jupiter's auroras. In fact, it plays a smaller role than you might expect. Where do most of the particles come from then? The answer lies in one of Jupiter's most volcanically active moons, Io. Io, as we discussed in Chapter 5, is a world constantly being squeezed and stretched by Jupiter's immense gravity and the gravitational tugs of its neighbouring moons. This tidal flexing generates tremendous heat inside Io, leading to intense volcanic activity. And what do volcanoes spew out? Among other things, sulfur and oxygen ions, electrically charged particles. Io's volcanoes are constantly erupting, blasting tons of these ions into space. These ions become trapped in Jupiter's magnetic field, forming a plasma torus, a donut-shaped ring of charged particles that encircles Jupiter. Think of it as a giant invisible river of electricity flowing around the planet. Now, here's where the magic happens. Jupiter's magnetic field lines connect to Io and its plasma torus. As Jupiter rotates, these magnetic field lines are dragged along, carrying the charged particles from Io with them. This process generates powerful electric currents that flow along the magnetic field lines towards Jupiter's poles. These currents then slam into Jupiter's atmosphere, colliding with hydrogen molecules, the primary component of Jupiter's atmosphere. Just like on Earth, these collisions excite the hydrogen molecules, causing them to emit light. However, because the energy involved is so much greater, and because Jupiter's atmosphere is primarily hydrogen, the resulting auroras are far more intense and energetic than anything we see on Earth. What does this look like exactly? Imagine a constant swirling curtain of ultraviolet and infrared light dancing around Jupiter's poles. While we can't see these wavelengths with the naked eye, spacecraft like the Hubble Space Telescope and the Juno spacecraft have captured stunning images of Jupiter's auroras. They appear as bright, glowing ovals surrounding the poles, with intricate structures and constantly changing patterns. But here's another fascinating aspect. Jupiter's auroras aren't just static displays. They're incredibly dynamic, changing rapidly in response to variations in both the solar wind and the activity of Io. Bursts of volcanic activity on Io can trigger dramatic increases in the intensity of Jupiter's auroras, creating spectacular displays that can last for hours or even days. Furthermore, the solar wind does still influence Jupiter's auroras, just not as much as Io. When solar flares or coronal mass ejections reach Jupiter, they can compress its magnetosphere, leading to even brighter and more dynamic auroral displays. Scientists have observed that these solar events can trigger auroral storms on Jupiter that are even more powerful than the usual auroras generated by Io. So we have two main drivers for Jupiter's auroras: Io's volcanic activity and the solar wind. But that's not all. There's another more mysterious component at play: Jupiter's own internal processes. Scientists have discovered that Jupiter's auroras also exhibit regular pulsations, even when there's no significant activity from Io or the Sun. The cause of these pulsations is still not fully understood, but it's believed to be related to processes occurring deep within Jupiter's magnetosphere, possibly involving the planet's rapid rotation and complex magnetic field. These pulsations create a sort of heartbeat in Jupiter's auroras, a rhythmic brightening and dimming that adds another layer of complexity to this already fascinating phenomenon. It's like Jupiter is putting on a light show choreographed to its own internal rhythm. What makes Jupiter's auroras even more intriguing is the type of light they emit. While Earth's auroras are primarily green and red, Jupiter's auroras are dominated by ultraviolet and infrared light. This is because Jupiter's atmosphere is composed mainly of hydrogen, which emits these wavelengths when excited. However, there are also traces of other gases in Jupiter's atmosphere, such as methane and ethane, which can also contribute to the auroral emissions. Scientists have detected faint traces of visible light in Jupiter's auroras, including red and blue hues, but these are much fainter than the ultraviolet and infrared emissions. Why is studying Jupiter's auroras important? Well, for one thing, they provide valuable insights into Jupiter's magnetosphere and its interactions with the solar wind and Io. By studying the auroras, scientists can learn more about the structure and dynamics of Jupiter's magnetic field, the flow of charged particles in the magnetosphere, and the processes that generate these powerful electric currents. Furthermore, Jupiter's auroras can also tell us about the composition and temperature of Jupiter's upper atmosphere. By analysing the different wavelengths of light emitted by the auroras, scientists can determine the abundance of various gases in the atmosphere and their temperature. And finally, studying Jupiter's auroras can help us better understand auroras on other planets, including our own. Jupiter's magnetosphere is a scaled-up version of Earth's, so studying the processes that occur there can provide valuable insights into the workings of our own planet's magnetosphere and the causes of auroras on Earth. The Juno mission, currently orbiting Jupiter, is providing unprecedented data on Jupiter's auroras. Juno is equipped with a suite of instruments that can measure the magnetic fields, charged particles, and auroral emissions in detail. These data are helping scientists unravel the mysteries of Jupiter's auroras and gain a deeper understanding of this spectacular phenomenon. So the next time you see a picture of Jupiter's auroras, remember that you're looking at more than just a pretty light show. You're witnessing a complex interplay of magnetic fields, charged particles, and atmospheric processes, a celestial dance of energy and light that is truly unlike anything else in our solar system. It's a reminder of the power and beauty of the universe, and the endless wonders that await us as we continue to explore the cosmos. Are you starting to see why Jupiter is so much more than just a big ball of gas? There are still many more surprises waiting to be discovered. What do you say we continue our journey and delve into another one of Jupiter's fascinating features? I think it's time we talk about Jupiter's role in the early solar system. What secrets does it hold about the formation of our planetary neighborhood? So you've seen Jupiter as a storm-racked giant, a magnetic behemoth, a protector of the inner planets. But what if I told you Jupiter is also a kind of time capsule, holding clues to the very birth of our solar system? You might be thinking, okay, now you're just making things up. You're going full sci-fi on me here. But stick with me, because the deeper we delve into Jupiter, the more we realize it's not just a planet. It's a cosmic Rosetta Stone. It's a dusty, swirling, immensely powerful Rosetta Stone, but a Rosetta Stone nonetheless. Imagine yourself, if you will, as a cosmic archaeologist. You're standing on the precipice of a dig site unlike any other, a site that spans billions of miles and billions of years. Your tools aren't brushes and trowels, but sophisticated spacecraft equipped with spectrometers, magnetometers, and a whole host of other meters designed to unravel the mysteries locked within Jupiter's swirling atmosphere and hidden depths. Think about it. 4.5 billion years ago, the solar system was a chaotic swirl of gas and dust. A protoplanetary disk, they call it. A swirling, chaotic mess, more like a cosmic Jackson Pollock painting than the neat, orderly solar system we know today. Picture a vast, flattened cloud of hydrogen and helium, laced with heavier elements, all spinning around the newly ignited sun. The sun ignited, and from the leftover material, planets began to coalesce, like cosmic snowballs gathering mass as they roll through the dusty landscape. Now, where does Jupiter fit into this primordial soup? Well, conventional wisdom says Jupiter was one of the first planets to form. And not just form, but dominate, to become the undisputed heavyweight champion of the solar system. You see, there are two main models for gas giant formation: core accretion and disk instability. Core accretion is like building a snowman. You start with a small core of rock and ice, and then you gradually accrete more and more material until you reach a critical mass. At that point, the gravity becomes strong enough to suck in vast amounts of gas from the surrounding disk. Disk instability, on the other hand, is a more rapid process. Imagine a dense clump forming directly within the protoplanetary disk, collapsing under its own gravity. A sudden, dramatic implosion, like a cosmic souffle collapsing in on itself. Which model is correct for Jupiter? The jury's still out, but the current leading theory leans towards core accretion, with a twist. It's believed Jupiter's core formed relatively quickly, within the first few million years of the solar system's existence. A cosmic blink of an eye, geologically speaking. This rapid formation is crucial because the protoplanetary disk wasn't going to stick around forever. The sun's radiation and solar wind would eventually dissipate the gas and dust. Think of it like a cosmic party that's winding down. The music's getting quieter, the snacks are running out, and eventually everyone's going home. So if Jupiter hadn't formed quickly, it might have ended up as a much smaller, less impressive planet, maybe even a super-Earth. Shudders. The thought is enough to send chills down the spine of any planetary scientist. A super-Earth around where Jupiter currently sits. The entire solar system would be radically different. But here's where things get really interesting. The composition of Jupiter's atmosphere suggests it swallowed up a lot of planetesimals, the building blocks of planets, during its formation. Imagine Jupiter as a ravenous cosmic Pac-Man gobbling up everything in its path. These planetesimals were essentially icy and rocky leftovers from the early solar system, like the crumbs and scraps left over after the cosmic feast. By analysing the abundances of different elements in Jupiter's atmosphere, scientists can get a glimpse into the composition of these ancient building blocks. It's like analysing the ingredients of a primordial soup to understand what kind of meal was being cooked. A dash of ammonia here, a pinch of methane there. Ah yes, a subtle hint of primordial chaos, a scientist might muse, staring at a complex spectral analysis. For example, the Juno mission has provided valuable insights into the abundance of water in Jupiter's atmosphere. Remember those water ice clouds we talked about? Measuring their distribution helps us understand how water, a crucial ingredient for life as we know it, was delivered to the inner solar system. Did Jupiter fling icy planetesimals towards Earth, seeding our planet with water? It's a tantalizing possibility, a cosmic delivery service ensuring that Earth had the essential ingredient for life to flourish. Imagine, a researcher might say to their colleague, Jupiter, the unsung hero of Earth's oceans. But Jupiter's influence on the early solar system doesn't stop there. Simulations suggest that Jupiter's gravity may have played a crucial role in shaping the asteroid belt. You see, the asteroid belt lies between Mars and Jupiter. It's a region populated by millions of rocky fragments, ranging in size from pebbles to dwarf planets like Ceres. But why didn't these fragments coalesce into a planet? Why are they just a bunch of cosmic rubble? The answer, it seems, lies with Jupiter. As Jupiter grew, its gravity stirred up the asteroid belt, preventing the planetesimals from gently colliding and sticking together. Imagine a cosmic dance floor, where Jupiter is the overzealous DJ, constantly changing the music and bumping into everyone, preventing them from forming any meaningful connections. Instead, they were flung around at high speeds, resulting in destructive collisions that shattered them into smaller pieces. Jupiter, in essence, acted as a cosmic bouncer, keeping the asteroid belt from becoming a fully fledged planet. "No planet formation allowed," Jupiter seems to shout, its gravitational influence echoing across the solar system. And there's more. Some theories even suggest that Jupiter underwent a period of planetary migration in the early solar system. Imagine Jupiter, not in its current orbit but much closer to the Sun, a hot Jupiter scorching the inner planets with its proximity. As it spiraled inwards, it would have scattered planetesimals and disrupted the orbits of other forming planets, a cosmic wrecking ball, leaving chaos in its wake. Then something happened, perhaps interactions with Saturn, that caused Jupiter to reverse course and to migrate outwards to its current location. A cosmic U-turn, averting disaster for the inner solar system. This Grantac scenario, as it's sometimes called, is still debated, but it offers a compelling explanation for several mysteries in the solar system, such as the relatively small size of Mars and the distribution of different types of asteroids. It's like Jupiter was playing a cosmic game of billiards, a scientist might explain, scattering the balls across the table and rearranging the entire setup. If Jupiter really did migrate inwards and then outwards, it would have had a profound impact on the entire architecture of the solar system. You're talking about a complete reshuffling of planetary positions, a cosmic game of musical chairs with planets scrambling for new orbits. So how do we unlock these secrets from Jupiter's past? Well, missions like Juno are providing valuable data about Jupiter's atmosphere, magnetic field, and internal structure. Juno's our eyes and ears on Jupiter, a mission controller might say, sending back invaluable data that will keep us busy for years to come. By carefully analysing this data, scientists can refine their models of planet formation and test different scenarios for the early solar system. It's like piecing together a giant jigsaw puzzle, with each piece of data bringing us closer to the complete picture. Future missions could potentially delve even deeper, perhaps by sending probes into Jupiter's atmosphere to directly sample its composition at different depths. Imagine the insights we could gain from analysing the chemical makeup of Jupiter's atmosphere, layer by layer. It would be like reading the rings of a cosmic tree, each ring representing a different period in Jupiter's history. A Jupiter atmospheric probe, someone might suggest. JAP for short. Catchy, right? We can also learn a lot by studying Jupiter's moons. The Galilean moons, in particular, offer a diverse range of environments, from the volcanic hellscape of Io to the potentially habitable subsurface ocean of Europa. By studying these moons, we can gain a better understanding of how Jupiter's gravity and radiation environment have shaped their evolution. They are like miniature laboratories, each offering a unique perspective on the Jovian system. Think about Europa for a moment. Its subsurface ocean is believed to be in contact with a rocky mantle, creating conditions that could potentially support life. If life exists on Europa, it might have originated from the same building blocks that formed Jupiter itself. Studying Europa, therefore, could provide clues not only about the possibility of life beyond Earth, but also about the origins of life in our own solar system. Europa, a hopeful astrobiologist might whisper, the key to unlocking the secrets of life itself. Jupiter, then, is not just a giant planet. It's a treasure trove of information about the early solar system. By studying its atmosphere, its moons, and its influence on the asteroid belt, we can piece together the story of how our planetary neighbourhood came to be. It's a story of chaos and order, of collisions and accretion, of planetary migrations and gravitational interactions. A cosmic drama unfolding over billions of years. And as we continue to explore Jupiter, we're sure to uncover even more secrets about its past. Perhaps we'll discover evidence of a long-lost moon, or a hidden layer in its atmosphere. Perhaps we'll even find clues about the origins of life itself. The possibilities are endless, a scientist might exclaim, their eyes gleaming with excitement. Who knows what we'll find next? So the next time you look up at the night sky and see Jupiter shining brightly, remember that you're not just looking at a planet. You're looking at a time capsule, a relic from the dawn of the solar system, a giant, swirling, enigmatic time capsule. And within that time capsule lies the key to understanding our own origins. What will we discover next? Only time and continued exploration will tell. The universe, after all, is full of surprises. Have you ever tilted your head back, craning your neck to truly see Jupiter, that creamy swirl of a beacon dominating the night sky? Really looked at it, past the casual glance, and wondered if it held more secrets than met the eye? More than just being the heavyweight champion of our solar system, the planet that dwarfs all others. What if I whispered in your ear that Jupiter nurses a secret ambition, a cosmic what if that, had it come to pass, would have rewritten the entire saga of our planetary neighbourhood, turning our familiar cosmic address into something startlingly different? Jupiter is often branded a failed star. It's a phrase that sticks in the mind, isn't it? Evocative, a touch melancholic. But what lurks beneath that label? What does it actually mean in the grand scheme of the cosmos? Is Jupiter in essence just a giant sulking gas ball relegated to the sidelines of the solar system, kicking up cosmic dust motes in frustration and forever lamenting its inability to ignite its stellar engine? Is it a planetary drama queen, yearning for the spotlight it was never destined for? Not quite. The truth, as is so often the case when we peer behind the curtain of the universe, is far more intricate, more nuanced, and infinitely more fascinating than a simple soundbite. The failed star concept bubbles up from our basic understanding of stellar genesis, the breathtaking process of how stars like our sun are born. Stars, those distant suns scattered across the cosmos, begin their lives as colossal clouds of gas and dust, drifting through space like cosmic tumbleweeds. These clouds, often spanning light years, are pulled together by the relentless force of their own gravity. As the cloud collapses inward, it begins to spin faster and faster, like a figure skater drawing in their arms. This spinning motion causes the cloud to flatten into a swirling disk. As the cloud collapses, it also heats up. The immense pressure at the center generates tremendous temperatures. If, and this is a monumental if, there's enough mass packed into that collapsing core, the temperature will eventually reach a critical threshold, the point where nuclear fusion can ignite. Nuclear fusion is the ultimate cosmic alchemy, the process where hydrogen atoms, the most abundant element in the universe, are smashed together with unimaginable force to form helium, a slightly heavier element. This atomic collision releases staggering amounts of energy, a radiant torrent of light and heat that blasts outward, counteracting the inward pull of gravity. Voila! A star is born, a radiant beacon shining brightly for billions of years, fueled by the inexhaustible power of nuclear fusion. Jupiter, alas, never cleared that crucial hurdle. It's a gas giant, a swirling sphere composed primarily of hydrogen and helium, the very same elements that fuel stars, but it simply lacks the critical oomph, the sheer gravitational muscle, to kickstart the nuclear fusion party in its core. Imagine trying to ignite a roaring campfire with a single damp match and a soggy log. You've got the basic ingredients, wood and fire, but you lack the necessary conditions for ignition. The spark just isn't strong enough to overcome the dampness and ignite the larger fuel source. So just how much mass are we talking about here? How much more oomph would Jupiter have needed to transform from a planetary giant into a radiant star? Well, Jupiter is already a colossal world, a true behemoth in our solar system. It tips the scales at roughly 318 times the mass of Earth. That's a lot of planet. It could swallow all the other planets in our solar system and still have room for dessert. But to cross the threshold and become a star, Jupiter would have needed to be somewhere in the neighbourhood of 75 to 80 times more massive than it already is. Let that sink in for a moment. Imagine multiplying the already staggering mass of Jupiter by 80. That's a truly mind-boggling amount of matter, a quantity so immense that it's almost impossible to visualize. If Jupiter had managed to accumulate that critical mass, if it had crossed that invisible line and ignited nuclear fusion in its core, things would be drastically, irrevocably different in our solar system. For starters, we'd likely find ourselves residing in a binary star system. Instead of orbiting a single sun, we'd be bathed in the light of two. Think of the sunrises and sunsets. How incredibly cool, or potentially terrifying depending on your perspective, would that be? A binary star system, however, isn't all romance and double the sunshine. It would dramatically alter the delicate dynamics of the planets. The constant gravitational tug-of-war between the two stars would create a much more chaotic and unpredictable environment. Planetary orbits would become more eccentric, meaning they'd be more elongated and less circular. Imagine Earth's orbit stretching out into an oval shape, carrying us closer to the Sun during one part of the year and then flinging us far away during another. This increased eccentricity could lead to extreme temperature variations on planets, making it incredibly difficult, if not impossible, for life as we know it to evolve and thrive. Consider Earth, for instance. Our relatively stable, nearly circular orbit around the Sun is absolutely crucial for maintaining a consistent and temperate climate. It's what allows liquid water to exist on our surface, and liquid water is, as far as we know, essential for life. If Earth's orbit were significantly more eccentric, we'd experience scorching, hellish summers and freezing, desolate winters, possibly rendering the planet uninhabitable. Furthermore, the habitable zone, that Goldilocks region around a star where temperatures are just right for liquid water to exist on a planet's surface, would be significantly different and likely far more precarious in a binary star system. It might be smaller, more complex in shape, constantly shifting and changing, or even non-existent altogether, depending on the specific characteristics of the two stars and their gravitational dance. So ironically, the very fact that Jupiter didn't become a star might actually be a stroke of cosmic luck for us. It allowed our solar system to settle into a relatively stable and predictable configuration, providing a conducive and nurturing environment for the emergence and evolution of life on Earth. Perhaps Jupiter's failure was, in a strange way, our salvation. But let's not completely dismiss the idea of Jupiter as a failed star, as a cosmic dead end. Even though it didn't ignite nuclear fusion, it still generates a significant amount of heat. This heat isn't from the fiery furnace of fusion, of course, but from a different, more subtle process called the Kelvin-Helmholtz mechanism. As Jupiter slowly contracts under its own immense gravity, it converts gravitational potential energy into thermal energy. Imagine a giant cosmic balloon slowly deflating under its own weight. As it shrinks, the energy it possessed as potential energy is transformed into heat. This process causes Jupiter to radiate more heat than it receives from the Sun. It's like a giant slow-motion implosion that's been going on for billions of years. A planetary slow burn. Think of it as squeezing a stress ball. As you squeeze, you're doing work, and that work is converted into heat, warming the ball ever so slightly. Jupiter is essentially doing the same thing, but on a planetary scale, squeezing itself under its own gravitational force. This internal heat plays a crucial role in driving Jupiter's atmospheric dynamics, contributing to the powerful jet streams that whip around the planet, the massive swirling storms that rage for centuries, and the vibrant, ever-changing cloud patterns that we observe from Earth. Moreover, the failed star label serves as a powerful reminder of the delicate balance of factors that determine whether a celestial object becomes a star or a planet. It underscores the importance of mass, density, and composition in shaping the destiny of these celestial bodies, highlighting the subtle differences that can lead to vastly different outcomes. The story of Jupiter also prompts us to consider the vast and breathtaking diversity of objects that exist in the universe. From tiny asteroids, no bigger than a car, to massive stars millions of times larger than our Sun, the cosmos is filled with a dazzling array of celestial bodies, each with its own unique characteristics, its own unique history, and its own unique role to play in the grand cosmic drama. Jupiter, in its own way, represents a fascinating middle ground between a planet and a star, a testament to the boundless creativity and ingenuity of nature. Scientists are still actively studying Jupiter, probing its depths with sophisticated instruments and advanced computer models to better understand its internal structure, its precise composition, and the complex patterns of heat flow within its atmosphere. Missions like Juno, currently orbiting Jupiter, are providing invaluable data that will help us refine our models of Jupiter and gain deeper insights into the fundamental processes that govern its evolution. One of the key questions that researchers are grappling with is the precise composition of Jupiter's core. Is it a dense, rocky core composed of heavier elements like iron and silicon, as some theories suggest? Or is it a more diffuse mixture of heavier elements, blended with hydrogen and helium under immense pressure? The answer to this question could shed light on how Jupiter formed in the first place and whether it ever truly had the potential, however fleeting, to ignite and become a star. Another area of active research is the study of Jupiter's magnetic field. As we discussed earlier, Jupiter possesses an incredibly strong magnetic field, far more powerful than Earth's, generated by the movement of metallic hydrogen deep within its interior. By carefully mapping Jupiter's magnetic field, using sophisticated instruments on board spacecraft like Juno, scientists can probe the planet's internal structure and gain clues about the dynamics of its metallic hydrogen layer. Furthermore, future missions to Jupiter's icy moons, particularly Europa, will provide valuable insights into the potential for life beyond Earth. If Europa does indeed harbour a subsurface ocean, as many scientists believe, it could be a promising habitat for microbial life, sheltered from the harsh radiation of space and potentially warmed by tidal forces generated by Jupiter's immense gravity. So the next time you gaze up at Jupiter, that radiant beacon in the night sky, remember that it's more than just a big pretty planet. It's a celestial enigma, a failed star that holds within it clues to the formation of our solar system and the tantalizing possibility of life elsewhere in the universe. It's a reminder that even in the vastness of space, there are always more secrets to uncover, more mysteries to unravel, and more questions to ask. And who knows? Maybe one day, with continued exploration and relentless scientific inquiry, we'll finally understand all the what-ifs that swirl within the heart of this magnificent gas giant. What if indeed? The universe, after all, is full of surprises,